Okay, so with the mass of the coronavirus, um, we need to use exponential growth. And again, I thought after yesterday class doing it for methods anyway, I thought it might be useful to look at this article that I saw yesterday on Facebook discussing how we can change its trajectory if we can slow the infection down now. So essentially, they're talking about how often the number of infected people double. It's not in terms of how many people are in contact. I think at the moment, the way it tends to work is one person infects on average 2.3 people. So I guess that's two whole people in their arm, and that arm touches someone else, I guess. But in terms of the total cases doubling, we're looking at 1, 2, 4, 8, 16 people being infected. We've got some comparisons here in the article I sent through. You'll see some diagrams and interactions if you wanted to. But essentially these things are doubling every 2, 3 or 7 days. And we can see the tables here. So 1, 2, 4, 8, 16, 32 people being infected across the course of 0, 2, 4, 6, 8, 10, 12 days. This is occurring every 2 days, it's doubling. So after 18 days, we'd have 512 cases. If we keep going on like this, we're going to have 1,024, 2,048 and so forth, and very quickly we have a very, very large number of cases. If we can slow it down to once every week, after 21 days, we still would only have 8 cases. That's what we're looking at here. As opposed to, after 18 days, having 512 in this first case. So if we can slow the rate of infection, we can have a much smaller number of people being infected after a certain number of days. And that's the hope of all the isolation methods and the shutting down of businesses and everything, trying to slow this rate of infection. The reality is most people are still going to get infected unless they can find cures or vaccines pretty soon. But we're trying to minimise the number of people in one hit. Otherwise our hospital system will not cope, because I believe there's only about 2,000 ICU beds in Australia. So we don't want to be filling it up, and if we have it doubling every 2 days, it is going to really fill up really quick. But we can imagine we can slow it down like this over the course of 9 weeks. Of course, we have more than 512 already, but we can start slowing that rate down. This number will not climb anywhere near as fast. So in terms of the maths we were doing yesterday, we looked at the idea of exponential growth being given by A naught e to the kt. We know A naught's the original amount, so in our case here we're going to class that as equal to 1 for now, because we've got one infected person. So we're going to run with the model A equals e to the kt. Now for each of these values, each of these ones here are going to get different values of k. So let's find the value of k for this first one. So if I have t equals 1, you're going to have, not t equals 1, I should take that back, t equals 2. So we're doing the double every 2 days. After 2 days, 2 people are infected. If you look at the next one, after 3 days, 2 people are infected. And after 7 days, 2 people are affected. That's the 7-day doubling. That's the 3-day doubling. And there's your 2-day doubling. If we run with that, what we're going to end up with is 3 different exponential models for what's happening in the coronavirus. So we have 2 equals e to the power of k times by 2. If we solve this by hand, we'll find that this 2k can move out of the power and you get log base e of 2. And k therefore is 1/2 log base e of 2. Do the same thing with this one, we'll find 2 equals e to the 3k. So you get 3k equals log base e of 2, k equals 1/3 log base e of 2. And hopefully by the last one you can see what's going to happen here. We get e to the 7k times 7, and you'll end up with k being 1/7 log base e of 2. So with these 3 models, you get different values of k, this growth rate in here. So with 2-day model, you get a equals e to the 1/2 log base E of 2 times by time. You're going to have the 3-day model, A is e to the power of 1/3 log base 2 of t. And the 7-day model, you have A equals e to the 1/7 log base 2 of t model. So you can imagine 1/2 is bigger than a third, which is bigger than a seventh. So this is going to have the highest growth rate, the lowest growth rate. I can substitute some numbers in here. So let's compare things. So let's say we did up to 18 before for this one. Let's say when t equals, let's find the lowest common of the three of them. Oh, this is the lowest common of the first two. Let's say when t equals 24, not lowest common, but a common one. When t equals 24, this one you find a will be e to the power of 1/2 log base 2, log base e of 2 times by 24, which will give us a certain number of cases, which I'm not going to risk moving out of this into my case, so I'm going to quickly do it on a normal calculator. And you end up with 4,096 cases after 24 days. This one, when t is 24, you get e to the power of 1/3 log base 2 times 24. So the same thing happens. It's quite a big number already. You'll end up with 256. And over here, if you do the same thing, but with a 7 in here, so a equals 1/7 log base 2, e to the power of that times 24, you'll end up with a being 10.76, so we'll say 11 people. So within 3.5 weeks, in this first case, you got 4,096. Now, at this point in time, Australia are not quite that high, but just 2 weeks ago, the coronavirus was on the edge of our imaginations, and we had about 30 people in the state in Victoria. Now we have 600 within 2 weeks. It's starting to really quite climb, much faster than this one. So it's doubling faster than every 3 days, but maybe not quite as fast as this one. But imagine if we could slow it down to this. And this is what the social isolation idea is about. I'll do one more calculation to sort of hammer it home, I guess. Let's see what happens when t equals, let's just go to 30 and see what happens. This will also show us the limitations of mathematical models, because they can't always predict long term. If you can imagine, if I kept doubling every 2 days, it's going to be pretty hectic pretty soon. So doing that, we come out with a number of 32,768 cases. And that's what the US are finding at the moment. They have so many people. They're the highest infected country in the world now, and this is what's happening. They had 14,000 new cases overnight, and that is an insane number of new cases overnight, because their measures were not introduced fast enough or followed strictly enough by their people. And that's what's happening. That's what happened in Italy. It's also what has been happening in Australia, with their massive crowds at Bondi Beach recently. People are just not taking it seriously. And we don't need to panic. We don't need to get into bunkers forever, but we just need to be sensible and careful and care for others with what we're doing. It's about loving our neighbour, as Jesus calls us to, by not doing whatever we feel like for the sake of others. So you can see now, done when we have doubling every 3 days and then doubling every 7 days, we would end up with 19.5, which is approximately 20 people. So if we can reduce the amount of isolation reduce the number of people coming in contact, increasing isolation, we can reduce the number of infections so majorly. It's not funny. It would really help our health system to keep this one. Now, at the moment, Australia is somewhere between these two. we've really been having cases for the last, major spike in cases for the last 2 weeks. So that's 14 days. So we're somewhere between the double every 3 days and double every 2 days. We want to try to move ourselves back towards that way. And you look at some of the data in that article at the start, it shows you some of the countries have managed to start to slow, that's what they're talking about, slowing the curve. If I was to plot these 3 graphs on a calculator, let's try that. Let's see if it's going to work for me today. Add graph, so we're going to have e to the power of 1/2 log base 2 of x. Let's copy and paste that, so just redo it. Oops. Of course it won't let me redo it. I have to retype the whole thing by the looks of it. One more time, one more try. No, of course not. Let's make it hard for everybody. 1/3 times. Whoops, I do not want x there, I want 2 there. And the last one, e to the power of 1/7 all base 2 times by x. So with these 3 graphs, we can see already the orange one, which is every 7 days, is very, very different. So let's increase our scale here. Let's fit it, and we can see that in just 19 days down here, the massive gap. I don't think it's possible for us to get this orange line at this point. We'd love it to be. We've got more. The problem is we have more than one person. This is all based on one person 20 days ago, but reality is 14 days ago we had 50 people or 40 people in Victoria, so we've started at 40 and doubled much quicker. So we're probably starting more around this kind of time frame here. So we'd be starting from this graph here, which we know would be a translation of 40 of not 40 of about 15, 12 units to the left. So if I started the graph there, you can see what they're all equal to start with for this pink line. If I just increase it out to 50 days, you can very, very clearly see here the very, very wide gap between the two. You can't even see the bottom lines down there. This does show the problem with exponential modelling though. After 50 days, if we're doubling every single time, we've now got 3.5 times 10 to the 7, so that's 35 million there. We don't have 35 million people in the country. So this graph will only be suitable for a certain amount of time. I mean, if you think about it, that's for 35 million people, but we only have 25 million. There's going to be a point somewhere, let's say around, what's this, maybe 45 days. So I'll reduce that and make it, let's say 40. There is going to be a point somewhere around 40 days where what you're going to find is the number of people infected, that's just over 1 million people there now within 40 days. The number of people infected is so great that the infection can't find many new people, if that makes sense. So the more people are infected, the less people there are that are uninfected. So it's harder for the virus to come in contact with somebody who hasn't been infected yet. So what will happen is this curve will start, just instead of going up, it'll start to slow down naturally. Eventually reach an equilibrium where it can't reach the number of people it needs to, and it will start to go down again. And what will happen is there'll be more people who are immune to it because they've had it, so it won't be able to find as many people who are non-immune to it and are susceptible to it, and it'll start to decrease. And as more and more people, this is still people who have got it, but the rate will not increase anymore, start to decrease. And that's what's going to happen with the pandemic. So if we can not get this peak so high, if we can get a lower peak before it slows down, like for example this one here is very high very quickly, we can get it even to the same height but over a much longer time, our emergency services will cope, our health system will cope, and we might even be able to slow it down in terms of not having as many people infected, and therefore much less in the way of deaths. It'll mean longer term pain, unfortunately, in terms of job loss and in terms of economic impact.